All right, now let's get on the way with our first presentation today. Professor Malcolm Munro is going to talk about fundamentals of electrosurgery, part 1. Malcolm? Forward, backward, and PSI.
Super. Well, good morning. Thank you very much for letting me be part of this. The enthusiasm of this group is infectious, but I have a lot to go through. These are the disclosures. None of these really relate directly to what we're talking about. These are our objectives, and I'm just going to take the first one now, is to try to understand nomenclature involved in RF electrosurgery. Some of the words you heard in the pre-test perhaps were not familiar to you, and there is a whole list of words that I hope we'll actually never use again. We're going to try to wipe these from the vocabulary and replace them with other words that are more accurately descriptive about what we're talking about. For example, Bovey was a wonderful individual, but what we use now is an electrosurgical generator, or ESU. We don't cauterize. We actually think about the technique that we're going to apply, what tissue effect we want to achieve. We want to cut, do you want to coagulate, desiccate, or do you want to fulgurate? Electrodes. There are active electrodes and there are dispersive electrodes. And there are no return electrodes, there are no ground pads, and we'll explain why. And there's no monopolar or bipolar electrosurgery, there are just monopolar or bipolar instruments, and hopefully we can explain that for you as well. So what is radiofrequency electrosurgery? Well, it's really an intracellular conversion of electromagnetic energy to mechanical kinetic energy to thermal energy. So we have a double conversion. And the purpose of this is so that we can increase intracellular temperature to achieve one of these effects, or one or more of these effects: vaporization, coagulation, desiccation, or fulguration. Fulguration is really just a special type of desiccation. It's not cautery. None of this is cautery. So what's cautery? Well, cautery is the passive transfer of heat. So you heat something and you transfer that heat to the tissue. So branding is an example that we know about. That's an example of cautery. Well, let's look at a few little pieces of physics that we really need to understand. And I'm going to go through this quick table and describe current, voltage, impedance, power, and energy. And at the top, current is the flow of electrons past a point in the circuit. So it's measured in amperes, which is coulombs per second. Voltage is really a difference in electrical potential. So the voltage is measured in volts, which is joules per coulomb. Impedance is the amount of resistance, if you will, that a circuit or a part of a circuit has to the flow of electrons. In direct currents, we call it resistance. In alternating currents, we use the term impedance, and it's measured in ohms. Power is a work term, and it is the product of voltage and current, and it's measured in watts or joules per second. And finally, energy, as you know, can be neither created nor destroyed, and it's really the capacity of that force to do the work, and it's measured in joules or watts per second. And if we want to look at this in a different way, Roger Odell, who used to work for Valley Lab, came up with this water tower analogy to explain Ohm's law, which is that current is directly proportional to the voltage and inversely proportional to the impedance. So if we take this water tower and fill it with water, we have, if we open the spigot, a flow of water through that spigot. So if we think of the height of the tower to represent force or voltage, we think of the flow of water to represent current, and if we think of the diameter of that spigot can represent impedance or resistance. So if we wanted to increase flow, current flow, what we could do is increase the height of the tower, which is like increasing voltage. And so when we open the spigot, we'd have more flow. But if we encountered impedant tissue, for example, or we wanted to increase the impedance, we could narrow the spigot, and even though the voltage is the same, the amount of flow will reduce. So where do we encounter this surgically? Well, we encounter it when we have inherently high impedant tissue like fat, or tissue that acquires its high impedance like scarred tissue, or tissue you've already desiccated and coagulated. So what does an electrosurgical generator do? Here's one. What's it do? Well, it takes the current that comes out of our wall. In North America, it's 60 hertz, 60 cycles per second, and it converts it into an output, an alternating current output that's 500,000 times per second, 500,000 times. So that 500 kilohertz is really like the left side of your AM radio dial. In addition to that conversion, the generator allows you to control other things like wattage, indirectly the voltage, the duty cycle, etc. And we'll explain what duty cycle is shortly. All currently produced electrosurgical units are isolated. So what does that mean? Well, if we look at the top circuit here, it's an isolated circuit. There's an active electrode, a dispersive electrode, a patient, the wires connecting to the electrosurgical generator, it's isolated. In the old days, there was only really one wire, and the patient was grounded, the instrument was grounded, and the electricity had to get through ground. So you can imagine what types of voltages you might have needed. So why do we use RF output? Well, surprisingly, we actually can predict the effects on tissue, and they are controllable. Maybe even more importantly, it doesn't kill you. Because of the high frequency of 500,000 times per second with that oscillating or alternating polarity, nerves and muscles are not depolarized. So that's the key. Now, let's talk about currents for a second. So if we make a direct current, like the one that you used with your toothbrush or your flashlight in the last 24 hours, what happens is ions or electrons flow from one pole to another. So the polarity is fixed. So if you looked at it on an oscilloscope, you would see this. But with alternating current, the polarity is changing. How many times a second? 500,000 times a second. So on our oscilloscope, we would see this alternating polarity. And as a result of that, there is no net current flow. It's oscillating. So think of it as an oscillating polarity. Think of the electrons as moving back and forth like this, rather than flowing in a circuit. So what does our generator do? Well, there's a lot of complicated things they do, but they basically put out two waveforms. So if we look at that little circuit down there, the low voltage output, which in North America only is called cut, is low voltage, and the so-called pure cut, it's continuous output. If we look at the so-called coagulation output, you can see that it's modulated. It's only on with these short bursts that are much higher in voltage than the so-called cutting current that we used before. So let's look at this in a little more detail. If we go and set our generator at pure and activate our electrode, we'll get this relatively low voltage output. So what happens if we increase to 100 watts from 30 watts? The voltage goes up. What's blend? Many people think blend has something to do with dialing something on the coag side and something on the cut side. Not the case. All blend is a modulation of the so-called pure cut output. So if we set this at blend, dial it up to say 30 watts and turn it on, we see this modulated output. See the gaps? So there's no current there. So if you think about it with the power equation that you see in the bottom, to keep the power the same, if we decrease the current, the voltage will increase. So blended currents at the same wattage output have higher voltage. Okay? So what's the duty cycle? Well, if the unit is on all the time, it's 100%. But this particular situation, it's only on 50%. So we call that a 50% duty cycle. If we make it 66%, the voltage will come down a bit. If we make it 83%, it'll come down a bit more. And if we make it 100%, it's at that level. Now, what about the coag side? So let's say set this at 50 and turn it on. Notice here that the current's only on a very short period of time, 6% duty cycle. So that means that we have to have much, much higher voltage. So this is the explanation about why there's much higher voltage with the coag output at the same wattage than the pure cut. We'll show you this in the lab today. Now, all electrosurgery that you do is bipolar, all of it. What differentiates the systems is the location and the purpose of the second electrode. So let's look at this. Here's a monopolar instrument setup. So we have a dispersive electrode, that's one electrode. We have an active electrode, that's two electrodes, bipolar. We hook them up to the machine, and then we activate the machine, and the current oscillates between those two electrodes. Now, in a bipolar instrument, what happens? Here's our same patient. We don't need a dispersive electrode because both electrodes are in the hand instrument that we're using. In this case, they're both active, and the only part of the patient that's involved in this circuit is that between the tines. And this explains why there are greater opportunities for current diversion and complications with monopolar, because the whole patient is between the two electrodes. Now, what about the mechanisms whereby RF energy causes these effects in cells and tissue? So let's just review again tissue temperature and effect. Normal is 37, right? Between 50 and 60 degrees centigrade, cell death occurs in between 1 and 6 minutes. So at 60 degrees, it's almost instantaneous. At 50 degrees, it takes about 6 minutes to get to cell death. Between 60 and 90, we have instant cell death, and we have these two processes called desiccation and protein coagulation. And when we get to 100 degrees centigrade, we get a liquid gaseous conversion, and we get vaporization. We're going to explain these. But first, we have to think about what's going on in this cell. So we have anions and cations in the cell. And if we put a direct current across this, okay, all the cations will go to the negative, the anions will go to the positive side. That's the so-called galvanic effect. And I'd love to talk to you for even 10 minutes about that, but I don't have the time. But what do we do when we have an alternating current? We have this oscillation. So think of these great big proteins in here going back and forth, how many times a second? 500,000 times a second. And so that's our mechanical energy being converted into thermal energy. And that's really the fundamental basis by which RF causes a tissue effect. It's not heating the electrode to pass the heat to the tissue, it's heating the tissue. Anytime the electrode is being heated, it's secondary to tissue heating. So what are these differences? Well, let's look at vaporization. So remember, we have this oscillation going on, and if we get our temperature above or at or above 100 degrees centigrade, we've already damaged the cellular membrane, and then we have this liquid gaseous conversion with massive volumetric changes, and so as a result, we get vaporization. And so we get this cloud, this plasma cloud of steam and ions. If, on the other hand, we keep the temperature between 60 and 95 degrees, we don't get that gaseous conversion, but we get two things happening simultaneously, and the first is desiccation. So water leaks out through this damaged membrane, and as the water leaks out, the cell shrinks, and so, of course, does the tissue shrink. But there's something else that goes on as well, because we have proteins in this tissue, in these cells, and so what happens is that we get hydrothermal rupture of the hydrogen crosslinks, and then as the tissue quickly cools, we get reformation or renaturation of these entangled, unwound collagen strands, and we try and hope to get a homogeneous seal, kind of like poaching an egg. So let's look at applications to surgery. Okay? Now, most of us as little girls or little boys spent some time in the backyard with a magnifying glass, and we took that energy from the sun and we focused it on a piece of wood and carved our girlfriend's name by focusing that energy until we got it so that it would burn. Okay? This is what you're doing with electrosurgery. It's really the control of power density. Power density is watts per centimeter squared, so the area of the electrode near to or in contact with the tissue is really what determines the tissue effect. So if we take these two hand electrodes, this blade here, and it's the same blade, and we take it on edge or on the side, and we take the same output, low voltage, we get a high current density or high power density in the edge contact and medium in the other side. And what do we get? On one side we get vaporization, on the other side we get coagulation. So in this video where this electrode is set at 50 watts, cutting, you saw it cutting with the edge interfacing with the tissue. Now we're just rotating it. And so will that cut? No, it's going to desiccate because it can't get that cellular temperature above 100 degrees centigrade. But then if we just rotate it back again, we can cut. No change in output, just the change in that interface, okay? So if we think about vaporization, really what we're doing is vaporizing tissue when we're cutting, and if we want to cut, we just do linear extension of that. So there's vaporization, here's desiccation coagulation. They can be done and should be done ideally with relatively low voltage outputs, and most of the time we want to use these types of cutting, so-called, or blend currents, although you can use a higher voltage current. And fulguration is this technique where we use very high voltage to essentially spray energy onto the tissue for superficial controlled bleeding. Cutting is a non-contact event, if you will. Desiccation is preferably by contact, and fulguration is non-contact. So let's go back. Vaporization and cutting. We vaporize. If we get linear extension, we cut. So cutting is linear vaporization. That's all it is. So this video is not showing a hot electrode cutting tissue. It's showing an electrode that's being used to throw energy back and forth between its tip and the tissue. That's what's happening in this video. Now, let's look at this sort of magnified. Because what happens is if you bring your electrode up to the tissue, you create that vapor cloud. And then as you move through the tissue, you should stay within it. If you get too fast, if you get beyond that vapor cloud or plasma cloud, you're going to get desiccation because you're going to have a lower surface area or higher surface area and get lower power density.
Perfect.
Okay? So there we are there. That sound shouldn't be on.
So you're wanting below our desiccation.
So just to have you think about that again. Let's move forward here. So desiccation and coagulation. So for formation of a sound vessel seal, coaptive coagulation should be performed slowly and only with low voltage output. Only with low voltage output, not the modulated high voltage coag output. This should be a take-home. So my residents for years have said you use cut to coag. I don't care what you come away with, but the low voltage is what you should be using to seal vessels. Why? Well, what happens is if you use the high voltage in this pulsatile fashion, what you do is each time you fire off one of those bursts, you get a superficial area of electrosurgical desiccation. Then what happens, if that burst comes back back again, it's non-conductive, high impedance. So the energy won't go through the tissue, and you'll preserve the deeper layers. Okay? On the other hand, if you use the low voltage output, you should get a homogeneous desiccation in a larger area. So to review this thought again, low voltage, what are we doing? We're desiccating cells, we're desiccating and shrinking tissue. And with respect to protein, we're denaturing that protein and then reforming it in a homogeneous fashion. And the result is, for vessels at least, a seal. And here's a video that I've now been showing for over 20 years. And it looks that old, doesn't it? But this is an old Kleppinger forceps. And what it's being used, and look at all the lateral thermal spread, and others will talk about that today. Look at all the lateral thermal spread with this. But what we're doing is we're desiccating the tissue. And as long as you can coapt, and as long as you can compress that vessel, you'll be able to cut it with anything. You don't have to have a fancy device. You can just cut it with a standard pair of hook scissors like this. Now, thinking of that, if you're going to get a vessel, and it doesn't matter whether this is laparoscopic or open or whatever, you have to compress the vessel. Why? Two reasons. One is if you don't compress that vessel, what will happen is the vessel will act like a heat sink, and it'll take the heat away from exactly where you're trying to target it. And secondly, if you don't compress the vessel, then the vessel can't seal. And if it can't seal on that interface, you're not going to get what you're looking for, which is hemostasis. So look at this again. If we use that cutting button to seal, it's hard for you to think about that, I know, but if you use that cutting button to seal, you get this homogeneous output and a good seal. If you use the coag button to try to seal, you'll get this spotty coagulation, preservation of some tissue integrity, and not only that, you'll get caramelization and sticking. And you've been through this, and you take the forceps off and it sticks and it starts bleeding. So high voltage will give you incomplete coaptive coagulation, superficial coagulation insulates the deeper layers, and caramelization and sticking. Last few slides. What factors affect lateral propagation of thermal injury? Well, there are a number. It's how much current you've got. Is it pulsed or continuous, and you can interrupt, and some of the people today will talk to you about interrupting that current a little bit to reduce the lateral direct thermal spread. High voltage versus low voltage will have an impact. And tissue compression, very important. So if we take these two pieces of tissue here and we put the same grasping electrode, this could be monopolar or bipolar, it doesn't matter, and we compress that tissue, notice that it is sealed much faster when it's thinner. And there's much less thermal spread than when it's very thick, because you have to apply more joules of energy to get the same effect. Well, our final area is fulguration, and fulgurate is from the fulgur, lightning. So you know this, you get this high voltage, intermittent bursts going from the electrode to the tissue, and this is sort of a graphical depiction of what it looks like. Arcing to the tissue, this is what we want to do, and it's really self-limited. If you don't touch the tissue, you probably won't get any more than about 0.5 millimeters in depth, 0.5 millimeters, because, as we said, it self-insulates. Okay? And so, fulguration, graphically depicted here, high voltage modulated current, no touch, large surface area electrode. Now, can you use this to cut? You can. And Randy's going to talk about that today, I know. In high voltage, or in high impedant tissue, you do need high voltage. You can dial it up by going to blend. You can dial it up by going to a higher output on your cutting side, and we can talk about what might be more or less safe there. Or you can use the inherent high voltage in the so-called Coag output. And this graphical depiction is really using an inert gas like helium, or in this case, argon, to actually help focus that energy on tissue. So there are your objectives. I hope we've met them. Thanks very much.
That was absolutely outstanding, Malcolm. Thank you very much.